All right, come on in. Okay, so the focus activity today is a little different. Does anybody recognize this? Yes, this is actually number 18 from the district assessment. What I did was this past Monday, I took all the data and I started going through it, and it was pretty consistent through all the classes. The most missed were numbers 4, 10, and 18, with this one being the highest. So I figured I'd go ahead and start with this one. Your next focus activity, which we'll probably get Monday or Tuesday, one of those days, is actually a combination of 4 and 10. Okay, so let's see here. It says a graph of a step function is shown below. Which key attributes describe the step function? So I think the best way is just to go through these one at a time and see how that eliminates the answers we have. One, the function is symmetric to the origin. Well, what does that mean if you have symmetry with the origin? That means what? Oh, you're close. It's an odd function. There we go. But I only want to rotate it halfway, only 180 degrees. So if I only rotate it halfway, am I going to get the same graph? No, not going to get the same graph. Okay, so 1 is definitely not right. So any answer with 1, we need to go ahead and mark off. Now 2, and I think this is the one that caught a lot of folks. It says the function is decreasing. Okay, unfortunately the function is not decreasing. Think about the definition, because I know it looks kind of strange because overall it has that downward trend, right? But think about the actual definition. It says as the values of x get larger, the values of y will decrease, right? So take a look at one function, or one step, I should say, like maybe this guy right here. So as the values of x are getting larger, so we have 0, 0.1, 0.2, we're moving along the x-axis, what are the y values doing? They're staying the same, which is how my step is created. So it would probably be more accurate to say something along the lines is that the function is constant on given intervals. Okay, something to that effect. So because the y's remain constant, it's not decreasing, even though overall it does look like it has that negative trend. Now with 2 gone, that means G is out, and if I remember correctly, I think G was the most commonly chosen answer. Okay, but can everybody see why? Does that make sense? Okay. You know, a problem like this, you take it one step at a time, you'll be just fine. Thought that would get a better reaction because it's a step function. Step by step. Hey, look, number 3. The domain of the function is, okay, now these are solution sets. We started looking at these the second week of school. Can you guys remind me of what they mean? Like, what's this vertical bar? Not equals, it was 2 words. Such that, okay. So all values of x such that x, what's that curvy E? Okay, equals, okay, that one, okay, belongs to is a member of. So x is all the real numbers. So is the domain all reals? Now that one's true, but I'm kind of confused because I'm seeing a lot of open circles. What's that, Nathan? That's exactly right. So while one function, one step function above says, I don't want to include the one below does include it. And, you know, we talked about condensing those intervals. So this guy is definitely infinitely wide. In fact, he still passes the vertical line test because even though it's hitting 2 points, remember one of those doesn't exist. Okay, so 3 is correct, but that really doesn't help me with these last 2 because they both contain 3. So it all comes down to 4. All right, the range of the function is all reals. Okay, so this one is not all reals. Okay, so that one is not a true statement. Because let's take a look. What we were saying horizontally, where one doesn't have a value, the other one does, right? So it's almost like we are using all those x's as we go through. But look vertically now. Okay, you're going to notice there are what? There are gaps. Okay, like this step right here, the only y value with him is -2. The only y value on this one is -1, 0, 1, 2. So in fact, I can't say all reals because, for example, there is no value of x I can plug in that would give me a negative 1.5, for example. Okay. In fact, does anybody see what set I'm creating? Remember, what set was created with the positive counting numbers, 0, and their opposites? Started with an I. No, not imaginary. Good one, though. Integers. There we go. It's the set of integers. So because 4 is out, F is the only one left. 3 is correct. Okay. Does that make sense? Does anybody have any questions on that? Okay. That one was definitely a little tougher. Okay. All right, so you have 3 focus activities now, and like I said, in the first 6 weeks, I only did 3 per each set, just basically because of the time we had, but I'm hoping to start increasing those numbers, so you'll definitely have a 4th next week, maybe a 5th if I can go ahead and swing it, but I'll let you know when we're going to turn those in. Okay, now we're going to talk more about angles and their measures. Okay. So if you've misplaced the notes or you don't have them, right over here by Adolfo, I do have extra copies. They should be in Thursday's folder. Okay. But we started talking about a lot of vocabulary yesterday, and you guys are going to have to remind me how far we got. But wherever you start to rotate, we call that the initial side. Wherever you stop rotating, we call that the terminal side. Okay, and of course, they're connected in what we call the vertex, which is usually going to be the origin of our coordinate plane. All right. And then we had a couple more ideas here. Now, where you start to rotate that initial side, if it starts on the positive x-axis, what do we call that? It was 2 words. Standard position. Okay, so if you begin to rotate from the x-axis, the positive x-axis, that's what we call standard position. So if you rotate counterclockwise, that's going to be a positive. If you rotate clockwise, that's going to be a negative angle. If you just begin to rotate anywhere else. Like, see, if you're putting it in a coordinate grid, we always want to use standard position. But realistically, if you were to say, okay, I have an angle 35 degrees, I could go ahead and draw these 2 rays and say that's 35 degrees, or I could even orient it differently. See, the standard position gives us a uniform way. We all know exactly where we're starting and how we're going to rotate. Okay, good. And then we talked about coterminal angles. All right. Well, coterminal angles, remember, they were angles that had different measures, but they had the same terminal side. They stop in the exact same position. Okay. Now, how many coterminal angles are there for any given angle? Indefinite. There's always an infinite number. Okay, because I can continue to rotate as many times as I want, clockwise or counterclockwise. So really, it's going to come down to my asking you basically what's one positive and one negative coterminal angle. So let's say, I'll give you another example here. Let's say I have theta, and theta is just a symbol we use to represent an angle measure, and there's a lot of different Greek letters we use. You can also see alpha, you can see beta, okay? But usually I think theta is kind of beta than the others. Math humor. Okay. All right, but let's say theta, that's the most common. Let's say I give you 50 degrees, okay? What quadrant would the 50-degree angle be in? First quadrant, okay? Because remember, we start at 0, then we have 90 degrees, 180, 270, and then all the way back around. One full revolution was 360 degrees, right? So let's say 50, is going to be maybe right here. Okay. Well, when you're asked to find one positive and one negative coterminal angle, all you're doing is adding and subtracting 360. So let's see here, 50 plus 360. Well, somebody help me out. What would that be? 410. So 410 degrees. So let me show you what this means. If I started here in standard position, on the x-axis, and I start to rotate, well, if I stop there, we already know that's 50, right? Okay. So I'm going to rotate all the way back around and stop on that terminal side. You see how I did the 50 with an additional full rotation? That's what we're doing here. So I know this would also be 410 degrees. And remember, that's why we have an infinite number. I could rotate another 360 and another. I could do that as many times as I wanted. Okay. Now, what would I do to find a negative coterminal angle? We go clockwise, so it'd be 50 subtract 360. 50 minus 360. Okay, so what is that going to be? What kind of 310? Negative. Now remember, we're not saying that the angle itself is negative. You're still going to have a 310 degree measure, but we're just saying it's how you rotate. So we're going to rotate clockwise. Let me do this one in green. I don't think it took that. So I would start here, and I'm going to rotate around until I hit that. That would be negative 310 degrees. Okay. That'd be the idea for coterminal. Now, if I wanted to go ahead and write an expression to represent every angle I could ever come across, well, in this case, I would say 50 plus 360 times n, where n is the number of revolutions that you have. So n would belong to, actually, we just talked about this group a second ago. Does anybody remember the z? Starts with an I. The integers. Okay, because you could rotate once, twice, 3 times, but you can also rotate -1, -2, -3. Remember, the negative is just the direction you're going. Okay, and then after that, we moved on to reference angles. Okay, reference angles were always created using the terminal side and the closest x-axis. Okay, so let me go ahead and give you, we got to these, right? Okay, just want to make sure because all the other classes were doing these as well. So if I were to go ahead, let's say I have theta is equal to, 205 degrees. Okay, what quadrant would the terminal side be in? Where would he stop? 1, 2, 3, or 4? Okay, 4? A little off. It'd be quadrant 3. Because remember, one full revolution is 360, right? So what's half of that? 180. And what's half of that? 90. So remember, every quarter turn represents 90 degrees, right? So what's 180 plus 90? 270. So if I'm looking for 205, yeah, definitely bigger than 180, but less than 270. So it's probably going to look something like this. This is 205 degrees. Okay. But now the reference angle, you always look at where the terminal side stops and the closest x-axis. This is what we're looking for. So how much further than 180 did I go? 25. So the reference angle here would be 25 degrees. Okay. That's all that means. Okay. So that's what we were talking about yesterday. Now let's really get into the trig. Okay. Oh, did we go over DMS? I did not show you 3B. Okay, let me go ahead and show you those very quickly on the calculator. And I'm hoping I mentioned this yesterday. If I didn't, it's really important that you know whether your calculator is in degrees or radians. Because if we're working with degrees, you want it in what? Degrees. Okay. If you're working with radians, then you want it in radians. Because if you're working in one, but your calculator's in the other, then that's going to give you some wrong answers. So a quick check, just go to your home screen. Okay. Right at the bottom, you want settings. Okay. And then document settings. And then as soon as it pops up, you see mine right here is in degrees. Now, if yours says radians, well, then just go ahead and click it, choose degrees. But don't click OK, click Make Default. Okay, Make Default. Because if you click OK, it'll go ahead and perform one operation how you changed it. But then after that, it'll revert back to what it was. So you have to make it the default. Okay. And even here, let me go to my home screen. You'll see at the very top of the scratch pad, it says DEG, so I know I'm in degree mode. Okay. Well, let's go ahead and take degrees, minutes, seconds. And I kind of walked you through yesterday how to do this by hand, but let's say I wanted to type this in. 36 degrees, 25 minutes, 18 seconds. Because we got our next quiz coming up this week. Okay, well, I should say next week. And part of it is I'm going to have you convert these. Okay. So I'm going to come on over here. So I'm going to type in 36. Now you're going to hit Control and use this catalog button right here below delete. It's the open book. And all these symbols, you'll notice in the top right corner, degrees is the one you're looking for first. Okay. Then I have, I believe it was 25, right? So the single tick mark is minutes. So after the 25, I'm going to go Control, catalog again. And you'll notice right here in the second row, there's that single tick mark. Okay. And now I'm going to type in 18, Control, catalog. Now, here's the thing. If you scroll down, there is a double tick mark, but don't use that one. That one is actually used for a different operation. So what we're going to have to do is just use the single tick mark twice. So I'm going to click it once, Control, catalog, click it twice. Okay. Now, as soon as you push enter, it'll go ahead and give you your decimal degrees. So my calculator is set to always give the fractional value. If yours is too, yes, just hit Control Enter. Control Enter. And see 36.4217. And that's exactly what we had right here. Okay. Now let's say we want to go in the opposite direction. This one is even easier. Okay. You take, in this case, the 42.575. I'm going to come on over here, 42.575. Now, you're going to use the same catalog button, but you don't have to hit Control. Just hit the catalog button. And you're going to notice this screen comes up with all of these tabs up here. You want the very first tab. So if that tab isn't open, you can use your touchpad. Go ahead and get the mouse, click on it. Okay. Now, even if your value is at the very top of the alphabet, if you click D on your keyboard, it'll automatically jump you to the beginning of the Ds. But what you need is DMS. Degrees, minutes, seconds. Okay. So I click that. Here's the command. It says take 42.575, change it to degrees, minutes, seconds. When I click enter, it automatically does that for me. Okay. And 42 degrees, 34 minutes, 30 seconds. Well, you'll notice that is exactly what we have right here. Okay. All right. So any questions on how to convert those in the calculator? Okay, well, let's go ahead and do this. Let me take this off real quick here. There we go. All right, so let's talk about radians. This is going to be really important when we're talking about trig. Okay, so another way to measure angles is in radians. In the late 1800s, mathematicians began to see a need for another unit of measure because they needed angle measures to cancel out. This type of measure is needed in calculus to help simplify certain mathematical and physical formulas. See, the problem is with degrees, you can't associate that with a unit of measurement. Isn't that right, Nathan? Not this Nathan, the other Nathan. Right. Okay. Because you don't ever hear anything like degrees feet or degrees inches. It just doesn't make any sense the way we do things. So we needed some type of measurement to go ahead and associate with distances because we want to know how far objects are traveling in a circular path. Okay. And that's where radians came in. Well, a couple things about radians. They have no units. One complete circular revolution. If I start in standard position and rotate all the way around, can anybody tell me how many radians in pi that is? If not, that's okay. It's 2 pi. One full revolution is 2 pi radians. Okay. So does anybody think they can tell me how many actual radians are in one revolution? And think about this. What's the value of pi? 3.14, right? But we have 2 pi. 6.28. So there are 6.28 radians in one revolution. But typically we like to just leave them in terms of pi. Okay? Probably because it's easy as pi. Okay. So let me go ahead and draw the rest of these axes here. All right, so let's kind of look at a unit circle. If one full revolution is 2 pi, well, what's half of that? Pi, right? Okay. Well, what would be half of pi? 1/2 pi, pi over 2. Can anybody tell me what would 3/4 of the revolution be in terms of pi? Think about it. What's halfway between 1 and 2? 1.5. Okay. So we like to say 3/2 pi, which is 1.5 pi. Okay. But now hopefully you're going to start to see from yesterday that certain radian measures and degrees have the same value. Like we start at 0 degrees. What's one full revolution? 360 degrees. So I know 360 degrees is equivalent to 2 pi radians. What would be equivalent to pi? 180. What do you think about pi over 2? 90 degrees. And 3 pi over 2? 270. There you go. Andrea, what do you think about that?
That's right.
Cool, right? Okay. Now, 1 radian is approximately 52.296 degrees. Okay, so what's below this, where it says the definition of a radian, that's how it walks through and tells you where we get that from. So again, like a lot of other math definitions, it's not as straightforward. So let me see if I can walk you through. Let's say you have a circle, like this one right here. The radius, the distance from the center to any point on the circle itself. Well, whatever the length of that radius is, if I could take that exact length and then find it along the outer edge of the circle so that I know this length is equivalent to this length right here. The angle created between the two, that's 1 radian. Okay, that's 1 radian. So let me try to visualize that a different way. Okay, let's try my hands. Okay, now the people at home will just kind of have to visualize this. So let's say that my hand right here, this is the radius of a circle. My wrist is the center. So my fingertip is where I touch the circle itself. So it goes all the way around, right? Now, hopefully, what are you going to notice about my 2 hands? Well, they are on top of each other, but hopefully they are the same length, right? Okay, got to hand it to me. Okay, so this length right here, remember this hand represented a radius. So I'm going to take that exact same length, and I'm going to find it on the outer edge of the circle. So the length of the radius is used on the circle. The angle created with that is a radian. Does that kind of help to visualize? Yes, sir.
So how do you measure the distance of an arc?
There are several different ways. How do we measure the distance of an arc? Now, back in the olden days, you were probably told to set up a proportion. Does that sound familiar? We are going to talk about this, but normally what I do is I take the measure of the central angle divided by 360 times 2 pi r. Okay, so let's say I had a 30-degree measure, and I wanted to know what the length of this arc was right here. And this is actually something that we're going to talk about in a later lesson, but since you asked, I might as well show you. What I would typically do, well, the measure that is associated with that arc is 30 degrees, right? So that's what I'm referring to when I say the measure of the angle. So I would take 30 over 360 times 2 pi r, whatever my radius was. Because this is just basically taking a portion of the entire circumference. Okay. Now, if I wanted to do the same thing for finding the area of a sector, well, then I would still take the measure of the angle over 360, but in that case, I would multiply by pi r squared. Does that look familiar to anybody? Okay, so kind of maybe some, maybe not. Okay, but that's okay. That's all right. But yeah, that is something we're going to be looking at, not the next lesson, but the one after that, when I look at linear and angular velocity. Okay, so that's a good question. In fact, some people out there might be thinking, well, why is one full revolution 2 pi? Like, where do we get that? And I'm really glad you asked that question. Okay. We use a central angle of a unit circle, shown at right, not left, where the vertex is the center of the circle. Well, let's talk about this. What's the formula that I just used for circumference? 2 pi r, right? It's also pi d, but because we're talking about radians, I'm going to stick with 2 pi r. Now, let's suppose that the radius of the circle is 1, and I want to know the circumference. Well, 2 pi times a radius of 1, what's 2 pi times 1? 2 pi. That's how we end up with our revolution. Right, Andrea? Right. That's how we go all the way around to 2 pi. Okay. And this right here is just a little tack on. In fact, what you were asking about, Angel, a second ago, this is a new formula we're going to start using in order to find arc length. So that's what S is. Okay, so S represents the arc length, R is the radius, and theta is your angle measure. Okay, you'll just simply multiply the radius times theta. But there's only one catch here. Theta has to be what? Has to be in radians. Okay. If it's in degrees, you're going to have to convert it. Okay. Well, let's see here. Common radian measures. Okay, well, let's go ahead and do this, and I think we'll go ahead and stop for the day because I do have some folks who wanted to ask me some questions. Okay. So let's see here. Negative pi over 4 radians. Well, let me set this up. Remember, we start at 0. 1 full revolution is 2 pi, right? But here's the thing. What's the negative tell me? How am I going to rotate? I'm going to rotate clockwise. So you remember how we said pi over 2, pi, 3 pi over 2? We're just going to reverse that like we did with the negative degrees. So this is negative pi over 2, negative pi, negative 3 pi over 2, all the way around to a negative 2 pi. I don't know why I put degrees there. Okay. So if you think about the fraction that you're given, just think about that as being a portion of what you're looking at. It makes it a lot easier to figure out where your terminal side has to be. So can anybody tell me what quadrant would negative pi over 4 be in? I heard 3, I heard 4, I heard 2. Now, negative pi over 4, isn't that equivalent to negative 1/4 pi? Okay, well, think about it. If I start here and I rotate only halfway, I've gone 1 pi, right? So really, we're only wanting to go 1/4 of the half. Okay. So right here, if I stopped, that would be 1/2 pi. So 1/4 is half of that, right? So right here, that would be negative pi over 4. 1/4 of 1/2. Okay. Can anybody tell me, where do you think pi over 2 would be? Well, now, would this one be in a quadrant? There you go. It would just be on the y-axis. It would just be straight up, right? Now, we actually have a name for these. If your terminal side stops on an axis, if it's not in a quadrant, we call this a quadrantal. Okay. So is negative pi over 4 a quadrantal? No, he's definitely in a quadrant, right? Only if the terminal side stops on an axis, okay, is it a quadrantal. Well, where would pi radians be? It's definitely a quadrantal. What axis? Okay, the x-axis, specifically the negative. So this right here would be pi. And why for these right here am I rotating counterclockwise? This first one we rotated clockwise. The first one was negative. The sign tells you how to rotate. Okay. All right, how we doing? Okay. All right, we will definitely continue to work with this on Monday. Okay. So good. Yes. Why is it negative if it says positive? Oh, you're talking about this one right here? I was just seeing if you were paying attention. And Lily Bell, I can't throw anything past you.